Go ahead.
Thanks, David. Hi, everybody. Hope you can hear me all right. So I'm Matt Madison. I'm going to talk a bit about the meta-tegra BSP, which is a BSP layer that I've put together over the last 5 years or so for the NVIDIA Jetson platforms. Let me talk a bit first about the Jetson hardware. And you'll hear the term Jetson and Tegra thrown around, and I apologize. It can be a little bit confusing. Tegra is the name of the systems on a chip that that NVIDIA developed, and Jetson is the name they gave to the modules that they built off those chips. So I tend to use the terms interchangeably, but technically there's a difference there. I'll talk about just the 64-bit Jetsons. I won't talk about any of the earlier ones because these are the ones that are currently supported. They all have a Tegra SoC, which has some number of ARM cores and an embedded GPU, and then some I/O as well, lots of I/O actually. The modules that they build include some peripherals, some memory, some storage as well. So the TX1 was the first. It came out in 2015. That was followed in 2017 by the Jetson TX2. This one is still currently supported. The TX1's been end-of-lifed. And you can buy a development kit that includes the TX2 module, as well as on a carrier board with power. And this one has Wi-Fi on it as well, and other stuff that you need to get going with developing with the Jetsons. The TX2 was followed by a TX2 4 gig model and a TX2i industrial grade model. More recently, in 2018, they came out with the Jetson AGX Xavier, based off their Xavier SoC that has a Volta GPU. This is their high-end unit. Includes 8 ARM cores of their own design. It's the Carmel cores, and lots of memory and lots of storage, and some deep learning accelerators. Then in 2019, they went low end, came out with the Jetson Nano, and that one has 4 gig on it, DRAM. They've come out now with a 2 gig stripped down model, which is roughly, I think it's $59 or something like that, to really target the entry level, sort of the Raspberry Pi type of consumer. And then midstream is the Xavier NX, which is based off the Xavier SoC, but is more targeted as kind of a replacement for the TX2. So they trimmed back the number of cores that they support. It has a smaller form factor, it consumes less power. It's actually some pretty powerful hardware, and it comes with a lot of software. NVIDIA provides a BSP that they call Linux for Tegra, and that's been around for a long time. It supported earlier revisions of the Jetsons and Tegras as well. Consists of a Linux kernel, all the bootloaders, the firmware, the drivers, power management stuff, basically everything you need to bring up the system. And then they also include that BSP as part of their overall JetPack collection of SDKs and tools, which really is what most people are interested in that are using these things, because it gets you access to CUDA, CUDNN for that's the neural network package, TensorRT for AI machine learning stuff, VisionWorks for their computer vision support, et cetera, et cetera. It's a big package of some big software. It comes with the tools that you need to get the software onto the device, which with the Jetsons, it's usually initially, and always has to be, in fact, initially flashed via a USB port. Uses special tools that NVIDIA provides, some are binary only, and there's scripts layered on top of that. It's very complicated because every single one of these modules works a little bit differently, and there's hacks all over these scripts to deal with all those differences. They do support secure boot on the devices, and there's additional scripts and tools that you need to have in place in order to be able to burn the fuses and then flash securely. So that's the BSP as provided by NVIDIA. There's the root file system that they provide for you to develop on is basically Ubuntu 18.04, which is maybe fine if you're going to try to set it up as a development station that you actually build natively on. But it didn't really fit very well, or doesn't fit very well into a typical embedded cross-build environment. As I was using back in 2015, when I first looked at this stuff, I was working at a company that already had a product. It was based on an IMX6 with some custom hardware for doing some computer vision stuff. We already had a Yocto-based distro that I was maintaining. And then I heard that the company was interested in possibly doing a next generation product that was based on this NVIDIA technology. So I bought myself a Jetson TX1 development kit and started looking at how I would adapt the BSP adapt their BSP into a Yocto style build. Then we definitely needed CUDA. We needed other hardware specific features from this stuff. So we needed to be tied to that hardware. But I didn't really feel like Ubuntu was a good base for doing an embedded distribution. So if you're going to do, so I decided to do my own BSP layer. NVIDIA wasn't interested in supporting open embedded Yocto style builds. They were happy with the Ubuntu offering they had. So let me talk a bit first about what a BSP layer typically provides. This is probably old hat for most of you, but it's the stuff that's board specific in terms of the kernel, the bootloaders, firmware, drivers. Typically have machine configuration files and any other board specific. So anything that's special about the images you need to create, board specific configuration files for sound or Bluetooth networking stuff, that kind of thing. And then often you'll see from vendor supplied BSPs, you'll see recipes for diagnostics or manufacturing tools. In meta-tegra, I've tried to basically follow that model. The kernel recipe in meta-tegra uses the kernel sources that are supplied by NVIDIA, which is a downstream kernel that looks like it comes from some Android products that they've been doing. They do provide the sources off a Git server that they host. It is a little bit unusual in that it's spread across about 15, maybe 16 now, separate repositories. So there's the core kernel, and then they have repositories for their drivers, the GPU driver, and a bunch of different repositories to host the different sections of their device trees that they have for these different devices. That was a little bit awkward to try and deal with from a recipe, so I came up with a mechanism using Git subtrees to basically reintegrate those 15 separate repositories back into a single repository that I host in a GitHub account. It's just a little easier to manage for building purposes and maintenance. And then I try to keep as close to their kernel as possible. I have had to do some patches, mainly for building with newer versions of the toolchain than they typically have used in the past. I think they were still using a 4.9 GCC to build things when we'd moved to GCC 7. So so backporting the necessary fixes for that from upstream, and then also there's always a few bugs, and so there's some bug fixes in there as well. These days, we do use the in-tree def configs that NVIDIA provides. I originally had a per machine def config that was hosted with the recipe, but somebody convinced me to switch to using the Linux Yocto tools to do config fragment management. And actually that's worked out really well. I was a bit resistant to doing that at first, but just because I didn't understand how the tools worked. But once I got the hang of it, it's actually made maintenance a lot easier. For the bootloader, it's a little bit complicated. There's some binary only parts of the boot chain that have to be provided. They do support U-boot on some of the devices. The TX1s and Nanos and the TX2s support U-boot. U-boot doesn't really do very much other than locate the kernel and the rootfs to boot off of. It doesn't really do much in the way of hardware setup. That's all handled now. It used to, but these days is all handled through NVIDIA's cboot bootloader, which is the actual secondary bootloader, and then U-boot is a tertiary bootloader. The U-boot support, they used to have an old downstream fork that they ship. They still ship from there, but somebody at NVIDIA has actually upstreamed all of their changes into U-boot mainline. So the latest recipes actually can track OE core more closely. The cboot bootloader is NVIDIA proprietary, but they do publish sources for that sometimes. So if you do need to do some customization of what cboot does, you can get the sources and do that. You just have to be careful that as they upgrade the BSPs, the cboot releases to match that tend to lag. The machine configurations in meta-tegra, basically, we've got configurations for all of the development kits that NVIDIA offers for these Jetsons, plus a few more for some of the non-dev kit modules or modules that are plugged into the development kits that aren't the standard ones. Because each of the modules uses has a different family of chip. I do make use of the SOC family support to try and group packages together and overrides together that are specific to the SoCs that might be common across multiple modules. And then recently added overrides for Tegra and a Tegra package arc for packages that are common to all of the Tegras regardless of which SoC they're using. It's complicated. And then as far as imaging and flashing goes, this was the hardest thing to get right. Just because it was hard to sort of reverse engineer how the NVIDIA scripts worked, but and plus the workflow is a bit different. The NVIDIA flashing tools assume that you pretty much assume that you can talk to the device as you're flashing, and then maybe make tweaks to the root file system and then send it over. Whereas for Yocto builds, we basically have everything available, everything built into the rootfs before we're done, and we can't do any talking to the device in between. So there is an image types BB class that creates a package called a Tegra Flash package. It used to be a zip file, now is a tarball that basically puts everything in there that you need in order to be able to flash the target. And then it's complicated by the fact that these modules come out with different revisions, and there's certain configuration files or device trees that are specific to the different revisions, and you need to know when you're flashing the device. You find out which revision it is, then you send down the right version of those configuration files. It gets a little bit hairy. So these Tegra Flash packages can be pretty big in terms of the number of files in them. For the devices, for the dev kits that have SD card slots, you can use the Tegra Flash package to generate an SD card that's plugged into your build machine, and then take that SD card and plug it into Jetson to boot it up. You just have to be careful about the bootloaders in that case. There's also additional handling for things like signing the boot components when you've got secure boot enabled, and for handling bootloader update payloads. They have a mechanism for doing what they call OTA updates, which is they provide a tool that runs on a device that takes a package in a particular format, picks out the right bits of the boot chain that need to be updated, and then sticks those in the right places, which would either be an eMMC boot block or QSPI flash, depending on which module you've got. Also, recipes in there for firmware and other services that support talking to the hardware. These things have very complex power management, and there's daemons that need to run to help with power management of the hardware. There's also some what they call driver libraries for dealing with hardware from user land where they don't have necessarily all of the smarts down in the kernel, and then a daemon for talking to or for getting input from cameras through their ISP that knows how to control the ISP. Graphics support's another complicated piece because, of course, this is NVIDIA. So they don't. So the typical, Mesa and for OpenGL and the stuff that everybody else uses, of course, we can't use that. The SoC does have a GPU and CPU combined, and they share the DRAM. The GPU driver is provided in source form in the kernel, but some of the userland components are binary only to deal with some of the special NVIDIA sauce there. There's a libdrm.so shim, and then they use the libglvend API and plug in their platform, their vendor-specific OpenGL provider under that. And of course, there's a special X server driver. There is some support for Wayland using the EGL streams patches. I can get West and Up. They use the EGL Wayland support that they developed. I think they still consider it experimental at this point, but it does work. And then they do have some Vulkan support, at least if you're using X11. And then on the multimedia side, they provide plugins for libv4L2 and for GStreamer for handling video streams from the cameras and to generate GL surfaces, mainly to deal with handling their NVIDIA memory buffers. They also have a specific multimedia API SDK for the Jetsons. It's just a bunch of headers and some sample code. The libraries themselves are part of the BSP. And then there's JetPack. So since people are using meta-tegra, are apt to need things like CUDA and so forth, there's a bit more than just a BSP in here, in that we also have recipes for basically unpacking the Debian packages that NVIDIA provides for their SDKs and repackaging them for the Yaka builds. CUDA is a little bit more complicated just because there's the host side tools as well. And the idea is you want to be able to build CUDA applications, cross-build CUDA applications. So there is a CUDA BB class in the layer so that you can configure and cross-compile CUDA applications. It does create some additional, there's some CMake modifications or some modules that are added to help with that. And it took a little while to try and get SDK support in, but that's there now as well. So you can build an SDK and have it have the NVCC be in there, and all the CUDA support, and have it just have, if you've got like a CMake based application, like say OpenCV, for instance, you want to add CUDA support, you can do that either through a bitbake recipe, and we do have a VB append for OpenCV that enables CUDA support. You can also create an SDK and cross-build your CUDA application that way. There are some dependencies on the toolchain version. If you use CUDA, CUDA only supports current version that they ship with the Jetson, only supports up to GCC 8. So that is a restriction you have to deal with if you're putting together a distro where you want to use this. You do have some virtualization support as well. That was added in revision 32 of Linux for Tegra, and thanks to contributions from Wind River, we got recipes in there. It will you can actually build the NVIDIA Docker support if you have the meta virtualization layer in place. And there's some Jetson specific container runtime pieces that need to be in place to make this work. For the Jetsons, NVIDIA decided that because the Jetsons by themselves don't have a whole lot of space, and some of the CUDA and other application libraries are really large, in order to save space, the Docker containers that NVIDIA builds for the Jetsons that are available from their NGC download site take advantage of the fact that their container support does a bunch of automatic pass-throughs from the host into the container of some of the core libraries. And so things like CUDA, TensorRT, a lot of stuff that's generally pretty big and would be really large to download into a Docker container, they're passed through from the host. But that means you can only run certain versions of the containers on certain versions of L4T. In order to help with some of the version compatibility problems, particularly around the tool chain, we added a contrib layer that's optional. You don't have to use it. You can, if you've got a way to build the older tool chains that you're already using, you can use that. But these recipes, basically forward ported from an older version of OE core, are there so that you can have GCC 8 available easily. And likewise, for GStreamer, their Docker containers, because it's their Ubuntu, they assume Ubuntu 18.04, that's still a GStreamer 1.14. So since OE core has moved on from there, you may need to build the GStreamer 1.14 in order to be able to support NVIDIA's Docker containers. And likewise, their DeepStream SDK, which recently was contributed by folks from RidgeRun, recipe for that. We ran into an issue where there was some compatibility with some of the binary-only components of the DeepStream SDK needing GStreamer 1.14. So we got recipes there to help with that. So this has been an interesting 5 years, and maintaining a BSP layer has been fun, but it's been a lot of work. It's helped that I've had real products at my day job in order to be able to give the BSP a good workout. Of course, it hasn't covered all the platforms, but at least it's given me a good way to test whether the BSP layer is suitable for real production use. I've been, and if one of the things that I've tried to be good about is tracking master OE core, and with the master branch I have and the BSP layer, that's been really good in terms of being able to deal with things like toolchain upgrades and other or graphic stack upgrades for which I needed to adapt. Doing those a bit at a time and tracking master along the way has made that a lot easier. I know a lot of folks tend to stick at a fixed long-term support version, for instance, for a long time, and then move over. I've done that for other projects in the past and have found that tracking the latest usually works better in terms of incremental effort involved in keeping up to date. I also have been trying to be really good about sticking as close to the stock settings from that NVIDIA provides with their BSP and not making gratuitous changes. And that's been good in terms of trying to track down when issues do crop up, whether it's an issue in the original BSP or whether it's something that happened in the layer. I do have automated builds set up. I've got my own AWS set up, and I do all my builds in the cloud. I do this automated with some test issues I have set up, and that's been helpful. I could do more if I had money to do that, but it's been enough without being too terribly expensive. It's also really helped me to have supportive employers that have let me do this stuff, even if it wasn't directly related to my work. But I've also learned a lot. This is hard. I know that I hear a lot of complaints about how bad BSP layers are, but they're really hard to do well, I think. It's easy to get focused on making sure that your platform works, and it's easy to forget that there are other machines and other architectures out there. One thing that I didn't know about until just earlier this year, back in the ELC North America, was the first I'd actually learned about the Octo check layer script, which I don't know why. I've been using this stuff for almost 10 years now, and I never ran across it before. But it's been a big help in terms of trying to catch mistakes, even though I've tried to be good about playing nice with other layers. It was a real helpful in tracking down some things that I thought I'd done right and hadn't. Putting machine-specific settings in machine.conf files. I started out when I did this as I wound up using a lot of overrides in recipes. And that worked okay initially, but really it gets harder and harder to maintain over time. So I tried to consolidate things into the machine configuration file. So when I have a new machine I need to bring in, because there's a new model, I've got all the settings right there. And that makes things a lot easier. Trying to keep the layer dependencies to a minimum with meta-tegra. It's only dependent on OE core. There are a couple of places where being dependent on meta open embedded maybe would have made things a little easier. I think I know at work it's worked out better to just have the core dependency, and I think other users have found that to be the case too. It also helps with keeping the number of permutations, combinations that you have to test against to a minimum. And then using existing infrastructure. When I first started out, I didn't worry too much about how the kernel recipe worked or how the U-boot recipes worked. But it certainly makes it easier to use the classes and the include files that are down in the core layer to provide some infrastructure for getting your builds to work, and it just makes things a lot easier for folks that are used to the way those recipes work for other platforms. And it's also the other thing I learned is the way I build things, my workflow, my configuration, whether it's at work or for my hobby work here, isn't the only one. Again, you get focused on getting your work done, and it's really hard to keep in mind that folks use this stuff in a lot of different ways, and a BSP layer needs to be able to work with, if somebody's really fixated on sysvinit, it's got to work with sysvinit, even if NVIDIA only supports systemd now with their BSP. the different packaging formats, SDK builds. There's a whole bunch of stuff that hopefully your BSP layer isn't affected by, but where there are touch points, you got to keep those in mind. As I said, these are powerful little devices. There's a lot of software available for them. They're complex. It's an ongoing challenge to deal with all that. Each platform is a little bit different, sufficiently different that sometimes it's difficult to make a change without breaking one of the platforms, so you have to be careful about that. The BSP itself from NVIDIA, their release process, let's just say could be a little bit more rigorous, run into regressions and just general quality issues, particularly with the tools from a release to release. Their support is through a forum, and you can, if you harass them enough, you can get them to provide fixes, but what they'll do is they'll just post something to the forum. They've started collecting those on the elinux.org wiki, so you can at least get links to patches that they have for the problems in their BSP. But it can take several months before it actually works its way into a new release, because these are big bang releases with supporting all the platforms, and typically they rev all the JetPack stuff at the same time they rev the BSP. Not always, but sometimes, most of the time. And then just keeping on this old downstream kernel with the Android patches and then NVIDIA's patches on top of that, the binary only problem, and the toolchain version issues. It's been a challenge over the years to manage that, and I'm sure that will continue to be the case. Although I have to say NVIDIA has at least released more sources for more bits of the BSP over time, and hopefully that's a trend that will continue. And then this whole dividing line between what's a BSP and what's really application support and what really belongs in a BSP layer. That's another open question that that I've had in mind here lately. So, and you really can build a BSP layer of your own. It's not a small task. The Jetsons are some very interesting and some very capable hardware. I mean, I'm working for a company now that's doing facial recognition type stuff so needs machine learning and AI. The hardware is well adapted to those kinds of applications. You don't have to use NVIDIA's Ubuntu-based software distribution if you don't want to, although NVIDIA doesn't seem too keen on supporting anything else, although they have partners now that will actually help with doing Yocto support for you. But if you're interested in the hardware and you're interested and you can live with some of the restrictions that we have with the binary blobs and stuff, it's got the meta-tegra layer to help you out. What's next for the layer? It's been mostly, if you look at the history of the layer on GitHub, we have multiple contributors, but I think my contributions are like 2 or 3 orders of magnitude higher than anybody else's. So I'd really like to get more active developers involved. We could use some more documentation on the project itself and how to use it and so forth. Love to add content. Love to make it easier for new folks to get started. And in fact, with the help of Dan Walks and Kurt Kiefer and some other contributors, we have a reference distro now, a demo that you can just clone and have a build setup that will build some images that have all of the necessary bits in them to exercise some of the cool stuff that we've got with this hardware. So if you're interested, please get in touch. You can find us on GitHub. We have a Slack channel for OE4T. There's an invite on on the wiki for the meta-tegra layer that will let you join automatically, or reach out to me by email. My email address is here. So thanks very much.